Welcome to the CBIA BizCast powered by Google. On this podcast, we dive into stories about Connecticut businesses.
Downs Construction actually came to my school.
And business leaders.
I think it's always also really important to be able to see a path forward.
We're shaping the future of Connecticut's economy.
Thanks for joining us for the CBIA BizCast. I'm Paul Pescatello, CBIA Senior Counsel and Executive Director of the Bioscience Growth Council. This week, we begin an important two-part discussion of a key issue in Connecticut and across the country, whole genome sequencing. A genome is a complete set of all the information contained in a person's 20 to 25,000 genes. Genes are made up of varying combinations of 4 chemicals that make up your DNA. There are 3 billion different combinations. Your genes and the 3 billion different combinations of DNA that make up your genes are the recipe, the code, the blueprint, so to speak, of life. Whole genome sequencing is a way for researchers and doctors to, so to speak, see a person's genes and identify variations that lead to different traits such as hair color or height and mutations that could lead to disease. As we will learn in both episodes, whole genome sequencing has become the gold standard in diagnosis of disease, especially for rare diseases, where before whole genome sequencing, diagnosis could take upwards of 7 years. Whole genome sequencing reduces that time frame to a few weeks. The latest technology, rapid whole genome sequencing, brings that time frame down to as few as 48 hours. In this episode, we are speaking with Dr. Tom Defay. Tom is a computational biologist and Deputy Head Diagnostic Strategy and Development at Alexion Pharmaceuticals. Alexion, based in New Haven, is AstraZeneca's division dedicated to rare disease medicine research and development.
We're pleased to have you. It's great you could be here. So let's just start right away by tell us a little bit about what you do at Alexion.
Sure. Again, Deputy Head of Diagnostic Strategy and Development. I've been with Alexion for about 8 years. I co-lead the Diagnostic Strategy and Development group, work on technology diagnostic strategies like bioinformatics, genetics, newborn sequencing and screening, with the aim of being able to diagnose individuals as quickly as possible to get them effective treatments.
We hear often about the diagnostic odyssey that rare disease patients face. Why does it take so long to diagnose a rare disease?
So in rare disease, the diagnostic odyssey can often take 7 to 8 years and seeing multiple different physicians. And in this time, the disorder that the patient has progresses. What we're trying to do is reduce that diagnostic odyssey so we get treatments to the patients as early as possible to maximize the effectiveness of those treatments.
Which rare diseases are you working on at Alexion?
So at Alexion AstraZeneca, we focus on diseases like hypophosphatasia, atypical hemolytic uremic syndrome, myasthenia gravis. These are all devastating diseases that our treatments have a really major impact on. And so we aim to again, identify these patients as effectively as possible and make sure we can get their diseases under control.
As you point out, it can often take 7 years to diagnose a rare disease. Often the rare disease patient is a newborn. A 7-year-old is a very different patient from a newborn. Whole genome sequencing seems especially suited to screening newborns, to figuring out an otherwise mysterious ailment. Isn't that the case?
So let me give you a specific example where speed is of the essence, and that's in the neonatal intensive care unit. So in this case, the child could be having 20 seizures an hour, and it's critically important to diagnose these newborns as quick as you can to figure out what's going on and potentially prevent a lifetime of impairment or even death. And whole genome sequencing has been shown to be critical in this situation.
And so going forward, I mean, how common is the use of whole genome sequencing?
It's becoming more common. So historically, it hasn't been that common, but in the last few years, we're already seeing 10 different states reimburse Medicaid for this rapid whole genome sequencing in the neonatal intensive care unit. So it's on its way to becoming the standard of care.
What is rapid whole genome sequencing compared to just standard whole genome sequencing?
So it's in the name. Rapid whole genome sequencing is rapid. A standard whole genome right now, you'd expect to get a result in, say, 2 weeks, maybe a month, depending on the situation. With rapid whole genome sequencing, you're typically looking to get a result within 24 hours or 48 hours. Now, at Alexion, we've contributed to 2 world records for fastest genomic diagnosis, first in 19 hours and then in 13 and a half hours. But we got superseded by another group, so currently the record is at 7 hours. So it can be done incredibly quickly if you're focused on how to do that work.
So why does it take so long? So, I mean, I think a lot of us are familiar with a CAT scan or an MRI. And so an MRI, which is longer than a CAT scan, might take 20 minutes or 30 minutes. But why does a whole genome sequencing take so long? Even a rapid whole genome sequencing takes hours.
So we're talking about billions of base pairs. So the first genome took.
When you say base pair, what do you mean by base pairs?
So your genome is composed, of course, of strings of nucleotides. These nucleotides code for those important elements of your body, like proteins. And there's not just a few of them, there's 3 billion of those nucleotides.
3 billion.
Indeed. And so sequencing that, the first time around when we did the human genome, took 10 years and multiple millions of dollars. Now, the fact that we can do it in 1 day and do it for even $100, depending on the circumstance, at that speed, it's going to cost more than $100, is remarkable. But it's still a significant effort to do all of that sequencing in that way and do the analysis, assemble the genome, analyze the genome. And then the key part also is the clinical geneticists to look at the preliminary results to make sure that they make sense.
So how does it actually work? What happens to the patient in terms of getting, I guess there must be a sample that's taken.
Yeah, so for the rapid whole genome sequencing, the sample is a heel prick. It's just a drop of blood. That's all it takes. And so everything else happens behind the scenes.
And so the drop of blood goes into a machine?
Essentially, yes. It goes into a completely automated machine system to develop that whole genome sequence, and then analysis of that sequence is in conjunction again with geneticists and physicians.
And so that machine is essentially a supercomputer that's analyzing all this data.
Essentially. But I want to emphasize that this has become a practical technology. This is something that we're doing every day. There are millions of genomes that have been sequenced now. So it's no longer sort of an esoteric technology. It's something that we know how to do.
It's telling you a lot of information. So how do you sift through all that information to hone in on the patient? And I guess also a subsequent question would be, what do you do? Do you save that data? It seems like it would be very useful to medical research.
So the key used to be just assembling that genome. But you're absolutely right. Now the focus has shifted to what you do with the data. And it depends a little bit on the context. So in the context of the NICU, where time is of the essence, we really do look at every gene. Well, the physicians look at every gene to understand which are the ones that are likely to be involved. And we marry the genetic data with our knowledge of genetic disorders and the variants that are associated with those disorders to find those genes that are likely candidates and then evaluate those. I will say that something that's starting to emerge is something called a newborn sequencing, which is rather than sequencing in the neonatal intensive care unit where the child is in distress, just sequence every child at birth and do it in a fairly automatic manner. In this case, we only pay attention, by we, I mean the Beginnings Consortium, not Alexion. So the folks who are doing whole genome sequencing only pay attention to those genes that are associated with devastating disorders that have treatments available. A number of individuals don't particularly want to have information about their whole genome either stored or shared with others. And so we only give back that information around those devastating disorders to keep it really focused. That's been the decision so far by the Beginnings Consortium and a number of other consortiums as well. And the reason to do that is to reduce the complexity and the concerns around what may happen with that data. So other data that may be around Alzheimer's or Parkinson's or something like that, we're not even looking for that information so we don't transmit it back to the parents. Now that data will be de-identified, and that de-identified data will be used to help understand both rare diseases and common diseases in greater detail.
What are the ethical issues around whole genome sequencing?
Well, the first practical one is we now have an effective technology. We want that technology to be available to as many people as possible. And it's really gratifying that, again, 10 states are reimbursing Medicaid for those procedures. That helps make it available very broadly to different people. That's the first piece. And a lot of that's driven by lower costs. Another piece is around sort of equity in terms of ethnicity. So there's some concern that since most genetic information is known about people of European descent, just to make sure it works in other populations. For starters, the baby bear population is largely Hispanic, 75% Hispanic. So the fact that it works effectively in that population is highly encouraging. We're also making sure to examine databases of adult healthy people and use that data to help understand how it works in different ethnicity. So we have a real focus to make sure that it helps well in almost all populations. As a personal example, I'm actually half Haitian, born in Puerto Rico. And many Americans have complex genetics. And we want to make sure that our medicines work effectively in everyone and that the diagnoses work effectively in everyone.
And there's also the issue of, right, that you might find someday a marker for Alzheimer's disease, and you tell the parents, the infant, we're going to be able to cure your child of this disease, but at age 60, he's going to get Alzheimer's disease. And that's sort of an ethics issue too.
Yeah, so first of all, it's all consent driven, right? So we consent the parents in any of these situations. And as I said, the situation for the newborns in the NICU is slightly different from general newborn screening. In general newborn screening, if we're doing it for everyone, the decision has been made to not focus on those sort of diseases of adulthood, only focus on those diseases of early childhood for which there are interventions available. So we'd explicitly not be reporting back risk factors for Alzheimer's disease. For the NICU screening, they are looking at all of the different variations. And so that information would be reported back. So first of all, doing the study, again, is consented by the parents, but that information would be reported back if it was deemed to be appropriate.
All the data that you're collecting and its use in research, just pure research, that's all consent driven. And when we say consent driven, meaning that patients are giving their consent or denying to use of their data going forward.
Absolutely right. So especially trials like the Beginnings effort is all consent driven, but that consent is upfront to say we can use the data for this set of activities and not those set of activities at the start. Over time, that may evolve, but it's always going to be consent driven. We want people to be empowered to own their choices and what happens to their data.
When you take a sample from a patient, like an infant, do you also take samples from siblings or parents to help in the diagnosis?
That is often done, especially in a diagnostic situation where there's an existing disorder. It helps to understand whether or not the variant is spontaneously arising or if it's genetic, and help rule out some potential false positives. So that's often done. In a number of cases, that's called a trio. And in a number of cases now, it's just going to be the blood spot from the infant and not the parents. So it all depends on the circumstance.
Can patients opt to sort of donate their genome, the data set of their genome for future research? Because I guess there would be genomic defects that you would find, and ultimately by comparing multiple patients, you could identify, this is a marker for a disease that there hadn't been a marker for in the past.
In many studies, the data is captured and shared in an anonymized way. As a matter of fact, one of the resources we use a lot is called the UK Biobank, where they have 1 million of these genomes that they've captured in the UK. It's been a tremendous resource to helping us understand genetic disease. And those types of resources are a really big deal. As a matter of fact, attaining these resources across diverse populations helps us make sure that we're developing tools that are going to be equally as effective in diverse populations. Great example of the story of Maverick, who came into the Rady Children's Institute suffering from seizures and spitting up blood. And he was very young at the time. and the doctors didn't know what to do. By using this technology, and it's again formed 2 years ago, they were able to diagnose Maverick in 39 hours. That diagnosis led to a treatment with, was it vitamin B6, which is routinely available, and was able to get Maverick's seizures under control. And I had the good fortune of meeting Maverick and his parents were very generous with their time at a conference that the Rady Children's Institute sponsors. And so he's 2 years old and he's doing fine. And being able to meet someone who the approaches and technologies that you've helped develop actually really helps is quite profound. It's a great experience.
And so what would have happened to Maverick? So you said it was at 39 weeks.
At 39 hours.
39 hours.
To diagnose.
So at 39 hours, if it had not been diagnosed, what would have become of Maverick?
So he was having a number of different seizures an hour. And that can be a big load on that child's cognition, their brain, their development. And so likely he would have eventually been diagnosed, but perhaps 5 days later, 6 days later. And in that time, there could have been permanent damage that was done that we're able to avoid.
So what's the future for genome sequencing? Will the machines get even faster, and will it become just routine that every patient, whether a newborn or a child or an adult, will everybody get genome sequencing?
So the cost will continue to fall, which is great.
And it's come down to about $1,000 now for not a rapid whole genome sequence, but it's just a whole.
I think 1,000 is a good estimate. If you look at consumables, the lowest you can get is about $100 now, but there's of course more that goes into it. So I think 1,000 is a good estimate. The rapid being a little bit more expensive, but the cost of consumables will become a smaller and smaller portion of this. The piece that you need to minimize is of course the cost of the physician's time, the geneticist's time, making the whole process more efficient. And we're working to do that. And I think what you're going to see is within a relatively short period of time, all the neonatal intensive care units will be offering this as an approach forward. It's proven, it's a powerful technique, it helps patients, and it lowers costs. What we're trying to do with the Beginnings Consortium, which is beginning newborn genomic sequencing,
Which is a sort of a nonprofit consortium.
Indeed. It's a consortium of 14 pharmas and biotechs with a number of different patient groups. What we're working to do there is first do the studies that demonstrate, like Dr. Kingsmore did with Baby Bear, the cost effectiveness of this solution. And the aim is to then expand this to all newborns. And there's a number of consortiums around the world that are working to do that.
Is whole genome sequencing and rapid whole genome sequencing, is it a cost-effective way to do medical treatment?
Surprisingly, it is.
Yeah.
So Dr. Kingsmore and team at the Rady Children's Institute of Genomics Medicine did a set of studies, starting with a study called Baby Bear, where they looked at sequencing in the neonatal intensive care unit. In this particular case, they only looked at individuals who had been identified as being likely candidates for genome sequencing because they were severe, they didn't know what to do next. When they looked at those kids, they were able to diagnose between 39 and 42%, looking at a variety of studies, of those kids based on the genome sequence. These are kids where we didn't know what was going on. And in over half of those, they're able to change clinical care. It turns out that changing clinical care in the neonatal intensive care unit is a surprisingly cost-effective thing to do because you help those kids go home sooner than they would otherwise. So not just being cost-effective, it actually saves money.
Yeah. So it saves time. There's less time in the hospital.
Yep.
And so before whole genome sequencing, as you said, for a rare disease, it could be a 7-year odyssey. So that's 7 years of going from doctor to doctor and hospital to hospital trying to figure out what's going on. So if you can do this, correct me if I'm wrong, if you can do this right away, early on, it's an incredible cost saver.
It is, and in this case, it can be a difference between spending, say, 3 weeks in the ICU versus spending 4 days in the ICU or 1 week. That difference can be an enormous amount of procedures that you don't have to do and cost and hardship for the patient. So being able to avoid just that NICU stay is enough justification. not even talking about that diagnostic odyssey for the next 6 or 7 years.
So we talked about Medicaid, and increasingly states are having Medicaid reimbursed for whole genome sequencing. What about private insurance and Medicare? Are those payers reimbursing for whole genome sequencing?
So it's really gratifying to see that private insurers are stepping up to reimburse specifically for this rapid NICU sequencing, because it's been so clearly demonstrated to be not just cost effective, but in many cases saving money overall and helping the kids. So private insurers are beginning to step up to take that load on. In terms of Medicare, unfortunately, I don't know. That's to my understanding, they are not yet covering it, but it may be in some cases they are.
But to the extent there's a trend of coverage for whole genome sequencing, it's what's driving it is that it's a cost saver.
It's either a cost saver or a very cost effective. In some cases, again, the newborn screening may not in the end be a cost saver, but is likely to be incredibly cost effective. I personally predict it'll save costs overall, but we'll have to see what the results tell us. And some of what we're doing here is running the clinical studies to see what's the impact on the health system, what's the impact on the kids, on their parents, their families, the whole story around what is the impact of what those studies are showing.
I mean, if it's cost effective in terms of identifying a disease, it almost has to be a cost saver, because otherwise you would spend so much time trying to, many more years, as we've talked about, many more years and so many other procedures and tests that the whole genome sequencing can identify immediately.
And part of what you're getting at is the rare disease odyssey is long and grueling and very costly. It takes a long time to understand what's going on, because rare diseases, if you have a disease that affects 1 in 300,000 people, in all likelihood, your physician will have never seen it. And so your symptomology may be really a big surprise. And so it's only after seeing the genetic connection that it all becomes clear. And that enables that diagnosis to happen in a far more rapid manner.
So before whole genome sequencing, that's an excellent point. It's something I think most people aren't aware of. So that an infant would present with a disease or malady, some set of conditions, and the physician may never have seen that, even if they've been practicing 30 years.
Indeed.
And so the genome sequencing allows that physician to identify something that they've never seen before.
Indeed. So let me tell a personal story.
Yeah.
So when I was 12, I was diagnosed with a rare disorder. It was a rare disorder that my mom had. If these technologies were available when she was young, she'd probably be alive today. That's pretty amazing. Not only that, I probably would have avoided the surgery I had, because it turns out I didn't have that disorder. And the genetics would have proven that. That genetic test only came out available when I was 19.
So tell us, how did Alexion, get into whole genome sequencing? How did it identify whole genome sequencing as something that would be valuable to pair to its medicines?
So I'm part of Alexion AstraZeneca now. Alexion got purchased by AstraZeneca. AstraZeneca has been looking at whole genome sequencing for some time and has been supporting whole genome sequencing in general. AstraZeneca was a very early investor in broad whole genome sequencing with the effort to get a better understanding basically about the biology and genetics of people around the world. So they were a big investor in things like the UK Biobank and Genomics England and these different projects to better understand as part of pre-competitive consortia. In terms of the Alexion journey, around about 8 years ago, I started working with Dr. Kingsmore. And I remember sitting down in the conference room talking about how we can help this leader in newborn care do better with his patients. And that's really where it started. There's a small group of maybe 4 people saying, how can we do this better? Mm-hmm. How can we make that happen? And it built from there.
How did that come to be that AstraZeneca chose to focus its rare disease research in Connecticut and in New Haven?
So first of all, Connecticut is where Alexion started. This is where Alexion comes from. And Alexion decided to house its center in New Haven and built a really pretty impressive research center. And so when AstraZeneca purchased Alexion, they said, well, what are the pieces we need to maintain? And one of the pieces they focused on was, we need to maintain that research center in Connecticut, in New Haven, because of the important work that they're doing.
I'm sure you do a lot of collaboration with Yale University.
Absolutely. So there's a lot of extensive collaboration with Yale University. A lot of really top talent has come from Yale University, but there's also work ongoing with labs at Yale. But as you say, there's work done with everyone around the world, not just at Alexion and AstraZeneca sites, but of course with institutions around the world.
So you obviously like what you do.
Absolutely. No, I mean, I think sometimes you get lucky. And in this particular case, to be able to spend your time doing work that helps transform the lives of newborns is fantastic.
Well, thank you so much, Dr. Defay. This has been super interesting and I think super valuable.
No, thank you. Really happy to be here.
Our thanks so much to Tom Defay. What a great description of how useful whole genome sequencing is and how it is truly a win-win technology, hugely valuable to patients for early diagnosis and treatment, and a cost saver for our healthcare system. We hope you will join us for part 2 of our discussion of whole genome sequencing, as we will dive deeper into how this technology is being used in a clinical setting with doctors Adam Matson and Louisa Kalsner, both with the Connecticut Children's Hospital and both experts in the field. Thanks to all of you for listening and watching. Remember, you can listen, like, and subscribe to our podcast wherever you get your podcasts. And please leave us a review and let us know if you have any ideas for future podcasts. And for a list of episodes, head over to CBIA.com.